So getting these results published in Nature, it feels incredible and feels amazing. I actually so I'm here at ICFO for 2.5 years. The 2 years have been spent on working on this experiment because of how complex it was.
As I said, it's a long journey, and that we can now play these games and use the full power of attosecond technology is extremely exciting, right? And of course, for the group, I'm super happy because many times it's a long journey to get to these results, and you fail many times until you achieve it. And I would say it's the cherry on the cake.
I mean, first of all, it's a big relief, right? Because finally this is like finished. You can actually stop and maybe continue on it later or do something else. The main result is that we can show that we can do valley polarization inside of a bulk TMDC material. This is different to the usual case where you have monolayer materials, monolayer TMDCs, that you shine light on, and with circular polarized light you can resonantly do valleytronics.
Electrons have more properties which can be used for processing information, for example spin or the valley.
Imagine a valley is like a surface, right? That has, for example, 2 bumps. These are the valleys. And you can imagine that like what you do with magnets, you can one orient up and one down. You can do it the same with the 2 valleys. If you have one valley which is, for example, lower than the other one, you could put some information in there. You can put electrons or charges in there, and they will be stored there. So you can have it like a 1, 0, or you could switch this, for example, in a 0 and 1. And so the idea is that you use this actually for information processing or information storage.
The previous usual efforts of manipulating or changing the valley polarization optically was to use a circularly polarized light. This method had several drawbacks because the driving light had to be gap resonant, and also for the method to work, the material had to be a monolayer. Our approach is to use a trifoil field, which in its shape matches exactly the shape of the triangular sublattice of the material which we use. In this way, when we apply it, the crystal that is, let's say, laser dressed in this field has a broken space and time symmetry, and this allows for control of the valley polarization.
At the first glance, it was not supposed to work because in these bulk materials, the 2 layers next to each other are oriented like this. And if we, let's say, select this finger in one layer, I would have expected that we would select this finger in the opposite layer, and that's going to ruin everything because the premise was we know how to grab that finger. And then it turned out that no, you actually completely controlled by the way you design light, which part of the material you're going to select.
This is a complicated experiment because you have 3 different laser beams that you all have to overlap in time and in space, and to get it all matching takes a lot of time, and you have to keep repeating it like basically every day to realign it.
So seeing the results that were at first contradicting the original theory was extremely exciting, but I think, of course, as a scientist, you don't immediately jump on, let's say, believing it, but you want to verify it. So on one side, it was definitely excitement. On the other side, it was double-checking everything in the experiment. Have we done everything correctly? Are we understanding it well?
I was surprised, but initially we didn't totally understand it, to be honest, because we saw the signature of this valley polarization, but when we studied it as function of time or how it would behave, we didn't understand all the details. So we had to go back to the theorists, to our partners. We were scratching our heads quite some time, and then we understood actually how the control was actually coming about. So it was not that we didn't see the effect of it, but the point was we didn't totally understand at the beginning how it could be induced in the specific material.
When the experiment worked, what we had to do simulations for the bulk material, and that took a long time. And really, we didn't even know if this was going to validate the experiment, but it did. And it surprisingly well validated the experiment. The outcome was a big surprise. The theory was on top of the experiment, and we didn't even try to fit anything. It's just the way it came out.
All your internet devices, your phones, for example, right? All the electronic circuits, you move charges, you move carriers across some junctions, and you do computations with it, and you need to store information. And currently about 10 to 12% of the global energy budget is actually spent for these operations. It's predicted to go to 20% in 2030, despite environmental problems, having to save energy and so on. So it's a big problem, and we do not have a solution really. So of course, science is busy trying to address this, and I cannot promise that what we have provided now is the solution, but it's probably one solution on that big puzzle. And I'm excited by it because it's a big problem that touches into everything basically, in computations, in information storage, in energy storage. And if this, the method that we have found, which is actually material independent, can be applied to it, I think it would be great.